Hi, I thought you might like to see what I'm up to. I got a microphone for recording video narrations. However, I can't just plug it straight into my computer because my computer only has a line level input. It doesn't have a microphone input. A microphone usually gives a signal of only a few millivolts, whereas a line level input needs a few hundred millivolts. So, I'm going to need a preamplifier. Now I could just buy one, but that would be boring. It'd be much more fun and educational to have a go at building one myself. So let's have a play around and see what we can come up with. I've positioned the microphone in front of my loudspeaker and put a video on to play to provide a sound source. Here I'm just connecting the microphone directly to the scope to see what happens. Turning up the sensitivity. We don't seem to be getting anything at all. It's as high as it goes. What's happening? To understand what's happening here, we need to look a bit more closely at how an electret microphone works. It has a piece of stuff inside it that has a permanent electric field kind of baked into it. It's called an electret because it's kind of like a magnet, except it's electric instead of magnetic. To make a microphone out of it, you put it between the plates of a capacitor. And if one of the plates is the diaphragm of your microphone, then when it moves you get a varying voltage generated between the plates. It's a pretty small voltage though, and it has a very high output impedance, which means it can't supply very much current. So the microphone usually has a transistor inside it as well to provide some buffering and amplification. But that won't do anything on its own. We need to supply it with a bit of power, which we usually do by connecting a resistor. Like this. And then we take our output from here. So all this stuff is inside the microphone, and we need to add that resistor ourselves. This is another reason why just plugging it into the computer doesn't work, because the line input connection doesn't have that resistor in it. I've connected some power to the microphone through a 10k resistor. Let's see what we get. Well, we're getting something. That's an improvement. It's kind of weird though. We've got this funny sawtooth. Looks like about kilohertz or so. I'm just going to disconnect the microphone for a moment and see what happens. Well, it's still there, so it's not being picked up by the microphone lead or anything like that. What happens if I hook the scope straight onto the power supply? Yep, it's coming from the power supply. Looks like we'll have to filter it a bit. I'm not sure how much I'm going to need. I'll start off with a 1k resistor and 33 microfarad capacitor. There's nothing magical about the number 33, it's just what I happen to grab. That looks fine now. Let's try hooking the microphone back up. That looks much better. Still quite low level though. Looks like we're getting maybe 40 millivolts peak to peak. We're going to need more than that, so we need some amplification. So let's talk about common emitter amplifier configurations. The simplest one looks like this. The emitter is connected directly to ground, and there's a resistor from the collector going up to the supply. Then we have a base resistor supplying a bit of bias current, also going up to the supply. The input comes in here, the output comes out of here. Now you want it biased so that the output voltage sits at about half the supply voltage, so it has room to swing up and down. The problem is that the value of base resistor you need for that depends highly on the current gain of the transistor, which is something that varies tremendously from one specimen of transistor to another. So you'd have to hand pick the base resistor for each circuit that you build. Now I'm only building one of these, so I could do that, but there is a better way. If you connect the base resistor to the collector, it provides some negative feedback which helps to stabilize the operating point. It still varies somewhat with the current gain of the transistor, but nowhere near as much. And our output voltage swing doesn't have to be very large, so it should be fine. The only remaining problem for us is that you don't get much choice about the voltage gain. If you do the maths, it turns out to depend only on the supply voltage. But we can fix that with another small modification. We can control the gain by adding a resistor to the emitter like this. Theoretically, the voltage gain should now be equal to the ratio of the collector and emitter resistors. It probably won't be because we don't live in an ideal world, but at least it'll give us a way of adjusting the gain. Okay, here's what the circuit looks like now. I've got a 47 ohm emitter resistor and a 4.7k collector resistor, and I've found that 1 meg base resistor gives me a voltage at the collector about 5 volts, which should be fine. Let's have a look at the output signal. That's a 200 millivolts per division, so it's definitely a bigger signal. Something about it doesn't look quite right though. Let's see what it looks like without any input signal. Looks like there's a bit of a ripple there. Yeah, that shouldn't be there. Let's try powering the amplifier from the filtered supply as well. That's a lot better. And here it is with the input connected back on. Time to find out if there's enough signal for the computer now. It's now connected to the computer using my highly sophisticated 3.5mm jack socket emulator. And that looks like quite a decent signal level. But the proof of the pudding is of course in the listening. So I came up with a historically appropriate test for a new audio recording device. Mary had a little lambda, its syntax white as snow, and every program Mary wrote, she wrote in Lisp, you know. Well, I don't know about you, but I think that sounds pretty good. Now I have to just tidy it up and make it more permanent. But I think that's enough for now, so I'll see you next time.